Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to do a bit more of these sort of storing energy in 3D prints, also called compliant mechanisms. And in this case, what we're going to do is we're going to make a 3D printed compliant or energy stored set of pliers or tweezers. Now, full disclosure, I think these are a little silly. In reality, you're not going to use 3D printed pliers for much. But it is a good exercise to better understand how we can design these flexible systems and we can build in the compliance or the energy storage into these mechanisms based on how we want them to move. So there are a couple things that we're going to talk about. We're going to try to relate these compliant mechanisms to essentially linkage systems. We're going to talk about ways in which they deform. And we're also, once again, going to use simulation to help us better understand what we should expect to see. All right, so in this case, I have two simulations run. This is load case 1 and load case 2. So with each of these, what we're going to do is we're going to play the results. We're going to animate them. And so in this case, for load case 2, I have the plier face fixed as well as the sort of square or hub that it would pivot upon essentially. I have that section fixed. And so what we're seeing here is when a load is applied to the handle, we're going to look here and we're going to see this outside section is straightening out. And so it's putting a load in this corner right here. And again, there's a large fillet there. And so what it's doing is it's straightening that section out. This section here is staying relatively stationary. There's not a whole lot of load going into it. Now on the back side of this, you'll notice that we're getting some load on the upper portion of this square. And that's because essentially what we're doing is we're pushing up on this section here, and we're causing a deformation of this upper link. And so again, as we look at this, in this case, again, the hub is fixed and the face that you would be grabbing something with is fixed. We are seeing a deformation in a couple of different areas. So this large arc section is trying to be straightened out. It's essentially put in tension, which means the point at which that curved section ends and it goes tangent to something else, we're going to see a spike in the load. And this is where we want to be careful. We want to make sure that we don't have a very small fillet in that area. And when we slice the design, we want to make sure that those areas have enough traces or walls on the inside. And then on the back side, again, we want to really look at the case where we are deforming the beam or a straight section of this design. And in the case of the upper section, because it can't straighten out like we have with the large arc, it is getting some bending and some deflection. And so this back section here is relatively straight, and we're pushing up in roughly that direction. So all the deformation is being isolated to that upper portion. Now I'm going to switch to load case 1. Now in load case 1, the handle is fixed, and the load is applied to the jaws of the plier, or that flat section where it would clamp. Now, I actually left the square section in this floating. I didn't fix it in space. And so the reason for this is because now we can again see the deformation. It is causing a bending in that upper link. There's a thin section here where it is causing bending there as well. And then this lower arc section is straightening out. It's sort of getting pulled in tension. Now, the reason I left the center sort of under constrained, I didn't fix it in space, is so we can kind of see what it wants to do if we are not fixing or holding this section in place. Now, a couple of things happen in this design. And so, for example, this section, the intersection here, is thicker than this outer wall here. And the reason for that is because I want the thinner section to have the deformation or deflection, and I want the thicker section to remain a bit more rigid or firm. So the inside of this design, even though it's sort of designed like this sort of coil or the spiral piece, the inside of this design, I want to remain relatively fixed. It's designed in a way that it can flex around and it can move as needed, but I really want to focus my attention on the outer spokes of the design. And so that's this large arc, which is going to be straightening out again as we deflect this. And this outer section here, which again, this back wall is roughly the direction of the force. So it's causing all of the bending to happen essentially in this section right here, this sort of small straight section. And that's how we're going to approach this in our design. Now, in the middle of this, I ended up using just a square section to lock them together. And I printed them at exactly the same size, so it's essentially a press fit. You could make a little bit of a gap there depending on your printer, but for the most part, printing exactly the same size will allow it to lock in place because you have the ridges of the layer lines and then the exact size, again, just kind of locks it in place. You can also put a little bit of glue on there if you want to. It's not really required because, again, I'm not going to actually use these for anything. It's more of a thought exercise on how we can design these types of parts. All right, so when we get started with a design like this, I do have intent-driven design turned on, so I'm going to be using part design. If you don't have intent-driven design turned on, you'll be using hybrid design, and you can just make everything with bodies. You don't have to worry about components in this case. But we're going to go ahead and create a new design. And then when we first start a new design like this, we have to figure out the scale. Now, that's the first thing. I actually made a set of these. I was not paying attention, and I made a set that was gigantic, like 180 millimeters across, because I was not thinking when I did it. But in this case, what we're going to do is we're going to start at the center, and we're going to start with a circle. Now, 25 millimeters, 1 inch is a good starting size. The next thing that I'm going to do is I'm going to make a horizontal construction line and hit escape. You can hit X on the keyboard, or you can actually toggle it over in the sketch palette. And then I'm going to make the portion of the design that is going to be the gripper portion of it. And so then I want to dimension this. I'm going to use 10 degrees. And essentially what we have is 10 degrees. I'm going to say coincident between this line and the origin, which will make it point at that. And now we basically just move the endpoints left and right for wherever we want. But 10 degrees is going to be a pretty good amount that we can flex the design. I don't know if the webcam is going to pick this up, but a pretty good amount that we can flex the design and have it pop back and not get into permanent plastic deformation. You could probably go more than this to 15 or so, but these are not going to be like a big set of channel lock pliers or anything like that. So really what I would say is 10 degrees, which will give you a max opening of 20 degrees, is probably about the limit that I would go for a standard PLA material. That's what I'm using for this. All right, so now that we've got this sort of the first part, we know that we've got a 10-degree section. We need to figure out how big this is going to be. And generally when we do this, this part isn't going to matter as much, but the distance that we go from, let me go to the dimension tool. The distance that we are basically from here to the origin, and then from the origin to where the handles are, is our leverage ratio. So if you're trying to actually make a set of pliers with some sort of force advantage, so if you want to, apply, let's just say 1 pound of force on the handles and you want 2 pounds of force on the actual clamping section, that's a, 2-to-1 ratio there. And so we're not going to worry that much about it for what we're doing, but, we do want to at least start to give these some dimensions. And so what I'm going to do is I'm going to use all nice round numbers. I'm going to say 5 millimeters between there. I do have some notes on sizes that I used for the one I 3D printed. I'm going to use 37.5 to there. I'm going to hit escape to get off my dimension tool. What I did to connect these hubs together is I just use a large arc, and mainly just to get it out of the way. And so kind of just make the arc. We'll come back and dimension that later. And then from here, I'm going to go perpendicular to that, come up at an angle. I'm going to go horizontal and then down until I'm tangent with this section here. And again, for our example, the dimensions for this outside stuff don't really matter all that much. So feel free to play around with the numbers. What I will say is that this 70 degrees is probably more critical. And again, that's simply because the force when we're actually pulling down on the handles, that's going to help the deformation sort of be focused in this upper area. And if you make this more vertical, then what you're going to end up seeing is you're going to start to see some bending, shifting around to different areas of the design. It might be a fun experiment to play around with, make it really steep. and then see what it does to the deformation, or make it straight up and down, or maybe even make it point backwards. But essentially what I'm doing here is, I've got the jaws at 10 degrees, and this is set in 20 degrees from vertical. And so I kind of just put those into that sort of area. And again, there's not like a math formula here that I used. It just kind of what felt right with a little bit of testing. The next thing we want to do is, again, just pick some nice round numbers. I'm going to use 27 and a half. I'm going to, let's go ahead and let's just make this 16 millimeters. For this section here, hit escape. I'm going to drag that a bit bigger. For this section here, let's go ahead and looks like it's about 60 degrees, so we'll make it 60 degrees. For this arc here, let's make it 18. And then I'm just going to give it a vertical distance from here. Let's just say 10 millimeters. And maybe make it a little bit smaller. And the reason I said make it smaller is because I don't want this section to be too thin, and I don't want to start to have some deflection here. All right, so that's the upper portion of it. The next thing we need is the handle. And so for the handle, if I'll put a little video on the screen, but you'll notice that I didn't just carry, well, on the inside, there's a little bit of a thin section that happens right in here. And that's intentional because, again, I want to use these to our advantage to control where the deformation happens. And so if you have got two thin sections of a design and one is a little bit thicker, the thinner section is the one that's going to deform, assuming that the force transfers to it. And so playing around with that idea or the intent behind that is something that you can just play around with your own designs and figure out. And so just kind of make the handle. We are going to make this 10 degrees, again, just the same as we did for the jaw. And the reason for that is because when they're the same, when the handles contact each other or they come close, that means this sort of two jaws of the pliers or vice grips or whatever is going to be the point where they're touching. So it kind of prevents us from squeezing them too much and breaking or overloading the design. And that's the main reason. And again, the distances here. So for example, we've got 37 and a half for the distance from here to the front. So if I click on that and multiply it by 2, it would be a 2-to-1. You can also manually make it whatever size you want. I wouldn't go too big because there's really no need. It's not like you're going to be putting a bunch of force on these, but I would say 90 to 100 millimeters is probably the max that I would suggest doing. And then I'm going to give this a vertical distance here. Let's just say 8 millimeters, and then hit escape. And what we're going to do is connect this with a big arc. Now, this arc here is actually kind of important. And the reason that it's important is because we're really looking at how we're transferring our force from the handle area into the rest of the design. So if I go back to these pliers here, and I just isolate one of these. So we've got this large arc at the top that transitions right into this shape here that we're stretching out. So when we're animating this and we're looking at the simulation results, and I'm going to go ahead and play this. And so basically, we want to carry that shape, that arc, and transition it into this thinner section. Because again, in reality, what we're doing is, unlike a traditional set of pliers, we're not just pivoting about a point. We're actually using some of the mechanics of the material to allow it to spring back. So we still are able to clamp onto things. And again, it will be limited by the amount of deformation that we can have in our material. But we want to make sure that we don't introduce a stress riser or an area here where we may potentially have a breakage. So I'm going to carry that over pretty gradually. And you'll also notice I kept the inside relatively thick there. And I did the same thing with a large fillet on this side, because what I want to happen is I want it to stretch that section out, and I don't want to load or put a load into that corner. And so the last thing that we really need to do is give this a radius value. 200 is probably fine. And then over here, I'm going to right click and say aligned. And I'm going to give this 7.5. That looks to be, visibly, it looks to be about right. All right, so now that's the base shape. We could go in and we could put all of the little details for the spring section or the hub section in, but honestly, I find it easier with stuff like this to extrude the base shape first and then come back with a secondary sketch. And the reason for that is because it allows me to easily try multiple things. I can suppress sketches and features and try a new one if I need to, or make multiple versions of a sketch and play around with it, not have it baked into that original. And so what I'm going to do is say -5 millimeters. I'm just going to go down, and then I'm going to add a fillet. And so on all of these sharp corners, so let's go here and here. Let's try 3 millimeters. All right, that looks pretty good. And so basically what we want to do is we want to take away or get rid of that sharp corner in all the areas where we're going to see some deformation. And so in this corner here and this corner here, these are the two main ones. This one not so much because it's always going to be in compression, and we're not really going to see a failure in the plastic in compression in that area. If anything, what would happen is it may cause the stress to rise across from it. But again, in this case, for a 3D print that thick relative to everything else on the design, it's not really going to matter. All right, so the next step in this process, when we're trying to figure out how we want this thing to deform, is if we go back to the carabiner example, which I don't have open right now, but if we go back to the carabiner example, which we did in the last video, we really looked at the difference or the way in which we wanted multiple pieces to flex and deform over a large area. So we don't want to have like a spoke that's going to be deforming right in the corner, because that's where we're going to quickly exceed our limit. Now, we did this example with our Q-tip blaster, and again, we did it with the carabiner and some other examples. And really, I found, at least for my types of designs, the best case is to really manage the flex of larger areas and transition those loads into those larger areas. And so when I started a design like this, I will begin with a hub section. So I'm going to say 5 by 5. That is going to be essentially the basis for the piece that's going to be coming up. It could be 4 by 4, could be 6 by 6. You just kind of have to play around with it. And so then I'm going to double click this and I'm going to offset it -2 millimeters. So anything that I want to flex in this design, I'm going to make a millimeter or 1.25 millimeters. Anything that I want to have the ability to flex, but not intentionally, I'll make a little bit thicker, 1.5, for example. And then anything that I really want to be more rigid, I'll make even thicker still, 2 to 3 millimeters. And so for a design like this, we'll go ahead and we'll just start with that. Then I'm going to do a circle, and I'm going to leave it underdefined for now. And then I'm going to put 2 more circles in here. And then we'll go to our dimension tool. And again, I want to control this section. This is the area that I want to flex. So I'm going to make it 1.25. The area that I want to be allowed to flex, but I want it to be a little bit more rigid, I'll make thicker, so 1.5. And let's just give it an outside diameter of 20. It's right about 20. And so I'm going to hit escape on here. And so what we have now is this is going to be cut away, and this is going to be solid in certain areas. It's not everywhere, but in certain areas it will be. And so now what we need to do is we need to connect this upper section to that ring and bring it down and back into the square. And then we need to do the same thing up here and bring it in and down into the rest of the body. Another thing that I did on this design is I offset this outside 1.25. Let's go 1.25, not 125. And actually, you know what? Let's do a little bit thicker. Let's do 1.5. And so part of the reason for this is, again, this little section right here is going to get thinner, which allows us to give it a point away from the corners that will introduce some additional deflection. And this is important, again, because it allows us to both control where the load is going, where the load is spiking, and where the deformations are going to happen. The other thing that we can do here is we can open up these areas to, again, allow for just a little bit more compliance. When things are extremely rigid on these 3D prints, that's when we start to force load into certain corners and areas, and that's when we start to see failures. And so what I'm going to do is I'm going to come over on this arc and come down to this inner circle here. I'm going to say I want these to be tangent and then coincident with the center. So it's always going to point down to the center. And then from that same point, I'm going to come out perpendicular and come up and hit escape. So that area is going to get cut away. It'll just be open and it will allow for additional flex. So basically, everything over here is thick and rigid. And what we're doing is we're controlling the point at which this upper section is going to start to deform, which will happen right here in the middle. So we'll need a large fillet so we don't have, again, a big load spike. And that large fillet will help shift the deformation into the section between this little thin area here and then that corner. So that will allow that corner to kind of bend and conform as needed. The other thing that we want to do is I'm going to grab another line tool and make sure that it snaps to that. We are going to make these two parallel, and I'm going to give it a dimension of 2 millimeters. So remember, anything I want to flex, I'm going to make this the thinnest part of the entire design. So 1¼ millimeters, which is going to be this outside section. Anything that I want to have the ability to flex, I'll make a little bit thicker. So 1½ I hit escape on my dimension here, but 1½ So I want this to have the ability to flex. And anything that I want to be more rigid and not start to flex, then I'll make it thicker. And so this 2 millimeters, basically this area coming up into the rest of the design, I want that to transition into the thinner section and allow the thinner section to flex and the thicker section to remain more rigid. And so we're going to carry that in. I'm going to go find the midpoint and bring that down. We'll use offset. I'm going to say symmetric and 1½ millimeters, which will give me an overall width of 3 millimeters, and then we'll turn that into construction. You'll notice with offset, it leaves these underdefined. It's okay, we can still use it, but it's a good idea for you to use the coincident constraint and go back and just make sure that those points are touching. Let's go ahead and repeat the process. On the top, we'll find the midpoint, bring this all the way up. There is a shortcut key for offset. Typically when I'm modeling, I use it. It's O on the keyboard. But if you're not comfortable with that, just know where things are on the toolbar. And again, coincident, we'll go ahead and do that. We'll put those together and hit escape. So the other thing I need to do is now this upper left section has everything we need. There's a lot of sketch profiles here. I am a big fan of having multiple profiles. It causes us to do a little bit more selecting when we're trying to extrude or cut things. But for the layout process, making sure that everything is fully defined and we can easily make things bigger or smaller, this to me is a benefit. If I start trimming a bunch of these edges, then I lose the ability to easily update these numbers, because then the arc over here might not be concentric and coincident with the arc over here. And so I just kind of avoid those. And so what I'm going to do is draw a straight line down. I'll draw a second one here and then give it some dimensions. And so the distance between these, this is going to be open. I'll make that 1 millimeter. It doesn't really matter as long as they're not touching. And then this is another area. I'm going to make it 1.5. I don't really want it to flex, but I want it to have the ability to flex. And so I know it looks crazy. There's a lot going on here. But now that we've got all these profiles, we can go to extrude, and we want to pick all the ones that we want to use to cut away. And so first I'm going to pick this upper section here. I'm going to pick some of these regions in here. So that one is going to go. Make sure there's nothing hiding down there. And so this is also going to go. This one will go. That one will go. That'll go as well. And we want to take out that little section. Again, I'm making that section thin intentionally. It doesn't necessarily make that much of a difference in this design, but playing around with things like this, like making one section a little bit thinner than others, can have a big impact on some designs. And so playing around with it can be important. And I'm going to make the center of that open as well. And then we'll rotate around and make sure that we go through all. All right, so now that is basically the design, but it's also very important for us to create these rounded sections with fillets. Starting with the largest ones is generally how I do it. And so, for example, this is a relatively thin section here. So I want to make sure that it has a nice large fillet. I'm going to add one there as well. I'm holding control when I want to go and add more to that selection. And I'll also round that section off as well. All right, so those are rounded off. I can go ahead and toss one up there as well. Remember, we are intending for this section up here to be the thing that's deflecting, and this section down here. All right, this is probably going to be it's probably going to be too large there. So what we're going to do is we're going to hit the plus icon, and then we're going to go back and add 2 millimeter fillets. So let's try to add 2 there. We'll go there, probably here. 2 is too big for that. I don't want to fill that much in. And let's, that's going to be too big there. It's probably the extent of the 2 millimeters because we don't want sections to get too thick. And actually looking at this, actually I'm going to hit OK. Looking at this, I think that section may be too thick. Let me go back to my extrude. Yeah. And so when I did this extrude, I should have also extruded those areas. It's going to give me an error on the fillet. I'm going to have to go back and make selections again. So this one here, going to have to add that. And then this one here, maybe add that. All right, and then we're going to add another one. This one on the inside will say 1 millimeter. And I'm just kind of working my way down with these sizes. Add one there. The stuff on the inside is likely not going to matter. So for example, these corners right here, these don't need much, if anything, because they're not really going to see any load. The only load that they would see is during the rotation is if there is a load caused by the square from one of these to the opening on the other. And in our case, it's not going to matter because there's going to be a little bit of a fillet there. And then we're going to add one more. This time it's going to be 0.5 millimeter. So again, just kind of working my way down. This one in here, that is 1 millimeter thick. So 0.5 millimeter is about all we can get away with. And that looks pretty good. And so just to kind of do a little bit of a recap, the areas that we want to be more rigid are the section around the square. We made it 2 millimeters. We made the top and the bottom of those 3 millimeters. And so really what I'm hoping is that there's no deformation in that center section, and it's forcing all of the deformation to happen either in this straight section here or in this section here, if there is any. And once again, these curved areas will tend to get stretched out and straightened, and the straight areas will tend to deflect in bending. And so as we plan these things out, it's very methodical and it's very intentional to plan out the thicknesses of each area. And remember, when we do the print slicing, we are going to have to play around with making sure that we have the correct number of walls and that everything is filled in properly. The areas that we want to deform are going to be the thinnest section, so 1.25 millimeters, because it's got a large section here and a thicker section up here. It will cause this sort of long, thin arc to straighten out and get pulled when we have the force applied to it. And then the back section here is just going to be a product of the direction of force. It is going to push up, in this case, in the positive Y direction on this section, which will cause basically to create a U or a bend in that upper edge. And so that's the basic process. We can add some more fillets. So for example, if we want to round anything off like this, you can. Does it matter for what we're doing? No, it doesn't. But obviously, if you're making your own design, then you want to have all of these things sort of built into it. Now, because both pieces are actually the same, we don't need to, like, if you want to assemble it in 3D, you can, but what we could do is just copy this body and make a version with the hole filled in and the post on top. But just so that we are familiar with it, again, I'm working in a part method inside of the intent driven design. If you don't have that turned on and you're in hybrid, these can all be new bodies, or you can make them components if you want. I find it easier to make them bodies at this stage. And so what we're going to do is we're going to create a mirror, a new body, and say, okay, I'm going to go into the bodies folder, use move copy, and move it up the 5 millimeters. And so that 5 millimeters was the height, the height that we made, or the thickness that we made the original part. And so at this point, again, remember the inside of this is going to be a 5 by 5. And the bottom one, I'm actually going to fill in. And rather than making any changes to the original design, what I'm going to do is select those, go to modify and hit delete. And then from my original or my second sketch, I can just take this and extrude it up 5 millimeters and join it to that body. And then we want to add a fillet. So I'm going to go to these vertical corners, and let's say 1 millimeter is probably too big, so I'm going to do 0.5 millimeter. All right, so now if we bring the other one back, you can see it's a perfect fit. And again, if we're printing this, it'll essentially be a press fit. If you need a little bit of a gap, you can, but what I would suggest is that you actually take this up higher than the second part and you flare it out slightly with a chamfer on the end, and that way you can press them together. You can also put super glue or some sort of CA style glue on them and lock them in place if you want to. But that's the basics of it. All right, and the last thing that we really need to do is, now because we're creating these as 2D to print, we need to get the jaws to be together. And the way that I did this on my design is I just added a line from here to here and then extruded that up 5 millimeters. So pretty straightforward, and do the same thing on the other one. Create a sketch, add a line. It's going to be perpendicular to that edge or parallel to this one. We'll extrude it. So E on the keyboard, 5 millimeters. And then round, let's go ahead and pull that over, round this corner off. I'll do the same thing on this one. And if you need to, again, you don't really need to for our design, but you can add a fillet there to kind of round things off. And then if you want to, obviously you can go crazy. You can add teeth to these things and add extra little features, whatever you want. For this example, I'm not going to do that. And there we have it. So that is the flex or compliant mechanism plier. And again, I don't think these things really have a whole lot of function in reality, but being able to think about this design, think about the compliant mechanism, and work it in a way that you can figure out where those deformations are going to happen, so that way you can make thinner sections or thicker sections and control where the deformation happens. Most of the compliant mechanisms that I see rely solely on bending of individual sections, and the way that they get around making these compliant mechanisms is to make those sections really long and kind of roundabout, go all the way around a design, and then you can get away with sort of those large deformations. But in reality, if we play around with where those forces are showing up, and we play around with, again, having these large arcs get pulled and straightened out through tension, and then controlling where the deformation happens and the amount of it based on the geometry, then we'll be able to apply these sort of methodologies to all kinds of different mechanisms. One thing I mentioned at the beginning of the video, which I don't think I really talked about, was treating these as linkages. Now, this is a much harder concept to think about, but if you're familiar with 4-bar linkages, and you're familiar with designing mechanisms, or you've played around with mechanisms that have pivots and links and things like that in them, then you can really go back to the basics of creating linkage systems. And instead of having a pivot, that's where you're going to be introducing deformation. And so with a system like this, the left-hand side of the pliers, we are going to have a pivot here, a pivot in the corner, and a pivot down here. And that allows those two pieces, the handle and the portion where we're actually clamping on something, that allows those two to have that sort of scissor effect. And then the fourth link between them would actually, would actually be the rest of the mechanism, the solid portion of it. And so if you can break down a design in that fashion where you can play around with it and think about things as links and not just as trying to deform a beam, sometimes you can get really creative and come up with ways to make these compliant mechanisms work. At this stage, there's not really anything else to the design, but what we're going to do is I'm going to push it to Bambu Studio and we're going to set it up to slice it. Now I've already printed the version that, I've actually printed several versions of these, but I printed the version that we have on the screen that we designed here. Let me go ahead and got to bring this over to this side. All right, so since they're two bodies in a single file, I can break them to objects. And then this top one, I'm going to put the flat face down on the build plate and then print them like this. I'm going to go ahead and slice it first so we can identify some potential problems. Get rid of the daily tip. And I'm going to just pull this down until we get into the design. All right, so the first thing that we want to identify here, basically the number of walls. So we've got 3 walls in that thin section where we do want it to deform. There is basically 4 in that slightly thicker section, the 1.5 millimeter section. And then you can see that we've got 4 in the outside here, and it combines to a thicker section where we want it to deform there. But the potential problem that we run into is as soon as we get out of those areas, we've got these voids here, and those voids can be potential areas for failure, and we don't want that. And so with a design like this, I would typically increase the number of wall loops, and then I would really look for this thick section, the 3 millimeter section, to be completely full, and to make sure that the areas around those transitions where we are planning or know that it's going to flex, we would just simply want to make sure that there is enough material past that point where we think it's going to deform. Now, if you're using simulation, you can identify that and then you can plan from there. There are also other things that we can do in terms of changing the type of infill or changing the some of the additional settings in whatever print slicer you're using. But I found the easiest way is to just play around with the wall loops. It doesn't have a drastic impact on the print time relative to, say, changing the infill density from 15 to 30% or something like that. And so playing around with the number of wall loops is typically my go-to when designing stuff like this. And again, the main thing I'm looking for is getting the walls to be past the point where I think it's going to deform. And so hopefully this helps. Again, I know I've had a lot of requests for compliant mechanisms, and in this case, I don't think that these are super useful, but it's a fun experiment to play around with and see if you can plan for the different types of deformation that you need for some sort of compliant mechanism like this. And if you want to print this one out, I'll put a link in the description of the video. I'll also toss this file on Patreon with the others from the last compliant mechanism. It'll be the exact same data set. I know I get a lot of questions from people that want like a donation link or something like that, and there's no other donation link. If you go to the merchandise store, I'll put a link to that in the description as well. But if you go to the merchandise store, there is a donate option there. But for this, if you want to buy the data set for $3 or whatever it is, you can. If you want to just download it from the description of the video, again, it's going to be exactly the same. So it's all up to you. But if you print these out and play with them, or you make any design changes, leave a comment and let me know what worked, what didn't, what changed. I'm just using a standard Bambu Hyper PLA or their standard PLA material for this. I don't really see much reason to go with another material for a design like this that, again, I don't see a whole lot of value in as a true tool, as opposed to just a metal pair of pliers. But again, it's fun to play around with and to try to figure out solve these problems with compliant mechanisms. So if you have any questions, let me know. If you want to see more of this kind of design video, let me know. As always, thanks for watching. We'll see you in the next one.